Welcome back to Calculus. Here is lesson 3.5, which is some shortcut rules for finding derivatives of trig functions. We're going to start with thinking about these graphs. Hopefully these graphs look familiar to you. We've got a graph of sine of x here and a graph of cosine of x. So try to copy these down, and on the same axes draw a graph of the derivatives for each of them. So in case you're not sure what to do, I'll get you started here. So for part A, I like to say that I like to start with finding where the derivative is 0. So the derivative of the sine of x is 0 wherever the sine of x is flat, and that's going to give you a point right here. So for example, f prime of negative pi over 2 is 0, so it has that point. And then over here, it's 0 again. In between here, it's going to be somewhat positive. You can draw a little bit more of it in there. And keep doing that for a bunch of points until you have some kind of thing that looks like the whole graph of each of these. And let's pause it now, because I will write the answers in and they will appear in 3, 2, 1. And here they are. Now, it might not look precisely like this. For example, it's hard to tell exactly just from the graph what f prime of 0 is here, the derivative of sine. It looks like it's approximately 1, because if you're going to draw a tangent line, it looks like it would have that slope, and pi over 2 is about 1.57, so it's kind of reasonable to say that this might be about 1 here, in which case the slope is about 1 over 1, so it looks like about a slope of 1, so that's not a bad guess, but you might have gotten something else. Anyways, then the derivative is 0 when x is pi over 2. Then over here, it looks like the slope is approximately negative 1, but maybe not exactly. That's the steepest point, though, and then it starts getting less steep, meaning the derivative gets closer to 0, and then the original function was flat here. That means the derivative is 0 there, then it's slightly increasing, so the derivative gets a little bit bigger than 0 until it's at its steepest point here, where it's approximately 1 again. And exactly the same kind of analysis happens with cosine of x. And so I just want you to know that we haven't really proven that I should say, the derivative with respect to x of sine of x at x equals 0. We haven't proven that it's exactly 1, but it looks like it's approximately 1. And also another way to see this is to use that GeoGebra, oops, that's the wrong one, that GeoGebra tool I put on the website, which here it is, okay. So yeah, I put this on the Canvas site, and now I just put in f of x is equal to sine of x, and you can move this thing around to get the secant lines between 2 points. So for example here, if you get 2 points that are on either sides of about negative 1.57, it looks like the slope is close to 0. And then if I get 2 points that are kind of on either side of 0 approximately, it looks like the slope is about 0.95, which is close to 1. But this secant line estimation of the derivative here is going to be a slight underestimate, because it actually gets steeper. It's at its very steepest point right here. So you can actually see the slight difference there. So maybe it actually is 1. Let's try to prove that, actually, that if f of x is the sine of x function, then f prime of 0 is equal to 1. So the way I want to think about this is, first of all, remember that we're always using radians in this class. So this sine of x function here expects x to be in radians, and if it's in degrees, a lot of things we do won't make sense. So wherever you see sine and cosine, just assume you're measuring your angles in radians. So let's actually just use the definition of the derivative to prove this fact. So that says that f prime of 0 is defined to be the limit as h approaches 0 of sine of 0 plus h, I'm plugging in x equals 0 there, minus the sine of 0 divided by h. And sine of 0 itself is just equal to 0, and so this becomes the limit as h approaches 0 of sine of h over h. So what this one we proved that this was equal to 1 before, but let's actually look at it a different way, because I think it will help to understand how these rules work and how radians work and that stuff in general. So so to do this, let's think about a small angle h. So this looks like a small angle h on the unit circle here. It's not that close to 0, but I don't want to draw it too small or nothing will fit. So this angle here is h radians, and we're on a unit circle. And the definition of radians, like what it means to be a radian angle, is the radian measure of an angle is actually just equal to the length of this arc length around the edge. That is equal to h. So in this case, I don't know, if I was going to measure this, well, the y-coordinate of this is like 0.55 or something. But we didn't go straight up, we went around a little bit longer, so I would guess that this h is a little bit more than 0.5, maybe 0.6 in this picture. And the y-coordinate of this point is what we call sine of x. So this y-coordinate here is, sine of h, sine of that radian angle. And you can also think of that as the length of this side, this opposite side of the triangle. That length is also equal to sine of h. Let me fix that. Okay, well, okay, so what you can imagine here, I can't really animate this, but if h was going to get smaller, if you're going to like drag this point closer and closer to a 0 radian angle right down here, then this vertical distance, which is the definition of sine of h, is going to get closer and closer to being the same as this curve distance. Here we can see that sine of h is a little bit less than 0.6. Maybe 0.55 or so, but that's because you went straight up to get that distance. But of course, the radian angle is going to be a little bit longer. But as this point gets closer and closer to being a 0 radian angle, like if the line was down here, then they would be almost exactly the same. And it gets closer and closer to them being equal. That means the ratio of them is going to come out to be 1. So that's exactly 1, because those are going to get to be the same thing the closer h is to 0. So yeah, that is a slightly more formal proof, not really formal, but an argument of the fact that this is actually equal to 1. It's not just close to 1. And this gives you an idea of what the formula is for the derivatives of sine and of cosine. So the graph of f prime of x, in this case, this is the derivative of sine, looks just like the graph of cosine. If you compare this one, oh, it's the wrong color. This graph here, it looks exactly like this graph here at all the same points. And so this suggests that the derivative of sine is cosine, and that is a fact. And also the derivative of cosine gives you this orange one, which looks kind of like sine in the sense that you have 0, 0 on it, just like sine does. But sine normally starts going up and then comes down again. This one goes down and then comes back up again. So this graph, in this case f prime of x, is actually negative sine of x, because if you just take the output of sine, like 1 here, and multiply it by negative 1, you'll get negative 1. 0 times negative 1 is 0. This negative 1 is sine of x here. If you multiply that by negative 1, you get 1. So that looks right. And so I just wrote these rules down here. The derivative of sine of x is cosine of x, and the derivative of cosine is sine. Now, yeah, remember this only works if the functions use radians. Let's actually think about what happens if we're using a different version of the sine and cosine functions to see how this is different. So I'm going to give it a different name so we don't get confused. I'm going to say g of x is this degree sine function, so sine subscript d of x. This function gives the sine of an x degree angle, and we're going to find a formula for g of x in terms of regular old sine, which uses radians, and find the derivative of this function. And we're going to see that it is not cosine of x. And this example I don't expect you to do. I'm just going to work it out right now because it's kind of a weird one. So what I want to do is convert this x to radians. Let's turn it into theta. So we're going to say that theta radians is the same angle as x degrees. So how can you get that theta in terms of x? Well, if you take, if x is 180, let's say, so this is the way I like to think about this, is a specific angle for x and then a specific angle for theta that's supposed to go with that. So 180 degrees goes along with pi radians. So what can I multiply x by? What can I multiply 180 by to get pi as the result? Well, pi divided by 180 should work. So if you multiply that fraction by x, you'll get a radian result. Because if that's the way I think about it, is plugging in 180 degrees for x and seeing that it cancels out and works. So that's that. And so this number here represents the radian measure of this angle. Now, if we want to write this function, g of x, in terms of the regular old sine function, if I'm not writing this subscript d, it expects this angle to be in radians for it to give you the proper results. So we're going to plug in a radian version of that angle. And then you can check that this works the way it's supposed to. So for example, if you do g of 90 degrees, that should be equal to 1. Let's just check that that works. If we do g of 90, will come out to be sine of pi over 180 times 90. And that 90 over 180 will cancel out to give you 1/2. So this is sine of pi over 2, when with regular old radian sine, you just get 1 there. So that's just me checking that this function does what it's supposed to do. So now that we have that, let's find the derivative of it. So to find its derivative, I'm going to use the chain rule here, which we need because there's an outer function sine of x and an inner function, the radian conversion function there. So let's write it like this. So, sorry, first we're doing the derivative of that outer function is the derivative of sine is regular old cosine. But what we plug into this is, it needs to be the original inner function, which is the way the chain rule works. And then we need to multiply that by the derivative of that inner function. And we end up getting cosine of pi over 180x times this derivative becomes just times pi over 180. And that is the answer to this. There should not be an x there. That's the answer to this. So that's why it's so important to use radians here, is because, and the reason we don't use degrees is because if you do use degrees for your sine and cosine functions, then their derivatives are these complicated things. So in other words, the derivative with respect to x of this sine sub d of x is this totally other thing here. It's not just regular old cosine of x. You could write this actually as this function here is known as the regular old degree cosine. If you plug in a number of degrees into this, this will convert it to radians and then do regular cosine. So we could call this cos d of x times that pi over 180. So either way, you get this extra pi over 180 thing, which makes it annoying to do these derivatives. So that's why we do not use degrees for sine and cosine. So let's do some more of these. I think you could try these on your own if you feel confident. I'll do the first one right now without pausing in case you just want to see one example. And then I recommend doing the other two paused. But if you do want to do them all on your own, you can pause it now and just skip ahead to see the answers. But let's look at part A. So we're doing the derivative of this function. Now, the way I see this is there's an outer function, which is 2 times sine of something, with a function composition where the inner function is 3 theta. So I'm going to write it using these chain rule colors. And so let's use the chain rule here. First, there's the derivative of 2 sine of something, which is just going to be, well, the 2 is a constant multiple, so you can ignore it, and then just leave it there. And then the derivative of sine is cosine, but then what is plugged into cosine is the original inner function, 3 theta, and then we multiply that by the derivative of 3 theta, which is 3, and then you can write this out as just 6 times cosine of 3 theta. And that's the answer to that one. You should definitely try these other two problems. I'll pause it now so you can give them a shot. And the answers will appear in 3, 2, 1. Here are those answers. So with the second one here, part B, the cosine squared, what that really means is that you're doing cosine of x first and then squaring the result, like so. So this is a function composition, and the outer function is the squaring, the power 2. The inner function is the cosine of x. So using the chain rule, we're going to do the derivative of the something squared thing is 2 times that something to the power 1. But then, and with the original inner function plugged in, multiply that by the derivative of the inner function, which comes out to be negative sine of x. So you, just to write it in a slightly nicer way, you get negative 2 cosine of x times sine of x. And then with this one, the difference is here, the x is squared, and then that result is plugged into cosine. So the outer function is cosine of something. The inner function is x squared. So here the derivative of the cosine becomes negative sine, according to the rule we just learned. And then using the chain rule, we leave the x squared plugged in and multiply by the 2x on the outside. Here's a couple of examples. I'm going to walk you through these ones as well, because they're kind of weird examples. But you might want to try these on your own. If so, you're going to have to pause it right now, and then when you're done, you'll have to fast forward to the answers to see that you got the right thing. Or you could just watch me do it again. Anyways, let's look at this. So this one is a sum of two functions. We can take the derivative of each one separately. And again, the outer functions with each of these, if you have sine squared of x, that really means sine of x with the result squared. And then we have plus the derivative of this. So the outer function is something squared, and the inner function is cosine of x. So let's work this out. So the derivative of this outer function here, the power 2, becomes 2 times that something to the power 2 minus 1, which is 1. So we're going to have sine of x in there, and then we multiply this by the derivative of sine of x, which is regular cosine of x. And over here, the derivative of that something squared is also 2 times something to the power 1, but with the original cosine of x plugged in, and we multiply it by the derivative of cosine of x, which is negative sine of x. And then let's look at what we got. Each of these has a 2 times sine of x times cosine of x. Here's a 2, a cosine of x, and times a sine of x. The only difference is this one is negative. So we're really going to get 2 sine of x cosine of x minus 2 sine of x cosine of x, which is also known as 0. Nada. So that's kind of weird. Is there an easier way to do this? Yes, the easier way to do this, easier, is only spelled with 2 e's instead of 3. But anyways, the easier way is that this derivative is equal to the derivative with respect to x of, let's think, is there a trig identity you can use to simplify this? Oh yeah, sine squared of x plus cosine squared of x is always equal to 1, no matter what x is. So actually, 1 doesn't change as x changes, it's just a constant, so its derivative is 0. So that's the shortcut way for that. If you notice that, give yourself a gold star, because this way is much more fun. Okay, so next let's look at the derivative of sine of x over cosine of x. I want to do this one because this is actually the same thing as doing the derivative of tangent of x, because that's a trig identity that tangent of x is always equal to sine of x over cosine of x. So to do this one, you can use the quotient rule. Actually, that's a good thing to practice, using the quotient rule right now. So actually, let's pause it here to use the quotient rule on this problem and these derivative formulas we just learned. And the answers will appear in 3, 2, 1. So here are those answers. So remember, we are really finding the derivative of the tangent function, because that's equal to tangent. Actually, yeah, I'm going to write a couple of these super important trig identities here. There's that one, and sine squared of x plus cosine squared of x is always equal to 1. These are the two trig identities that you absolutely really need to use and know all over the place. There's a ton of other trig identities that only get used every once in a while in math, but these two are like in every single math class you take, more or less. Not every math class, but they show up a lot. So anyways, we're going to use both these identities here. So we're using the quotient rule, so we're doing the original denominator times the derivative of the numerator minus the original numerator times the derivative of the denominator over the square of the denominator. I just wrote out the quotient rule, also known as low d high minus high d low over the square of what's below. It works out here, so you get cosine squared plus sine squared, which according to our most important trig identity ever is equal to 1. So just to summarize this rule here, this is the formula for the derivative of the tangent function, 1 over cosine squared of x, which you can also write as secant squared of x. I prefer to just use fractions instead of bothering with the secant and cosecant notation, but it's up to you. So those are the three main rules that we have from here: is the derivative of sine, the derivative of cosine, and this one. So those three things you need to know. So here's some practice problems to try. These are all a combination of the chain rule and the rules we learned today, and some other differentiation formulas. So give these a shot. Let's pause it, and the answers will appear in 3, 2, 1. And here are those answers. So the same sort of principles as before. By the way, if you got these all three right, excellent. You get a gold star. Yay. If you didn't, let's go over what I did here. So first of all, with this one, the outer function is sine, and the inner function is e to the power t. So the derivative of sine is cosine, like we went over earlier. The derivative of e to the t is e to the t. That goes on the outside, and the original inner function is plugged in here. With p2, the inner function is 1 minus cosine of x. The outer function is all to the power 1, the whole thing to the power 1/2, the same as that square root. So the derivative of something to the power 1/2 is 1/2 times that thing to the power 1/2 minus 1, which is negative 1/2. And then that gets multiplied by the derivative of the inner function, which becomes positive sine of x. Positive sine of x is what you get when you do negative sine of x. So the derivative of cosine becomes this negative sine of x, but then it was negative on the outside, so that's that one. And anyways, they cancel out, and you get positive sine of x. And you could also write it in this way if you like. Anyways, thanks for watching. I'll see you in class.